Hello, welcome to this tutorial series. It is keyed to a course that I teach at the University of Wisconsin River Falls on in econometrics. And we're going to begin with prediction and a little bit of an introduction to simple linear models. And we're going to focus on using the tool called R to do so. So brief introduction. In this tutorial, we're going to estimate a simple linear regression, make a scatter plot, do some of the basic diagnostics that we should do every time that we do a model, regardless of the technique. And then we're going to calculate a prediction of the dependent variable using that model. All right, so the first thing we're going to do is we're going to start out by we're going to import our data from R. And what I've done is I've set up a project. And in that project, there is a folder called data. And I'm going to use the read.csv file or read.csv command to load that data. There are numerous ways to bring data into R. This is just one of the ways, and I think a very, very easy way, especially if you're bringing data out of something like Microsoft Excel. You save the data as a CSV file, which is a very small file format. It's also human readable because it's in text. It's a text file. And R can very easily read that. All right, we're going to store it in an object called food. So think of this object food as a box. All right, I've got this box here. And in this box, all right, its name is food. And I can put stuff. And what I'm going to put in this stuff is the data that was in food.csv. So read.csv makes a data frame. Okay, makes a data frame, and we're going to put it in there. Notice I use an arrow. So in R, the assignment character, the assignment operator, is this arrow looking thing. And that's just the angle bracket or the less than sign and a dash. Okay, we use that, and you can think of that as it's just arrow. It's saying put the stuff here on the right and stick it into the thing that's on the left. All right, and the thing on the left is just a box. That box can hold stuff. In this case, it's going to hold what's called a data frame. Now, a data frame in R is kind of the basic unit that R holds data in. You can think of it as like one page out of an Excel workbook, right? It's this rectangular thing that holds a bunch of different data. And the different data can be different data types. So some of it could be text, some of it could be numbers, some of it could be Booleans. I mean, there's all kinds of things that you can put in this. The big thing is it's going to be a big rectangle, and really just think of it looking as like one page out of a spreadsheet program's workbook. Okay. Okay, so let's do a little bit of work here. I want to show you a little bit of fancy stuff, quote unquote, fancy stuff, that I like to do in order to make my stuff a little more portable. So the first thing I want to do is I want to show you what this food data looks like. All right, and to do that, I'm going to use a function called head. All right, so let's just break this down. I've got head. All right. And what that function will do, you can't really read it because my handwriting is terrible. Sorry, I've hurt my wrist and my writing was bad to begin with. What that function will do is show us the first few rows of the data. But of course, I'm a bit of a perfectionist and I wanted it to look pretty. So I'm going to use a package, all right, called DT. Now, the package DT just helps you present data frames or data tables and make them look a little prettier and do it fairly easily. Okay, but a bigger topic here is the fact that R, one of the most powerful things about R is that over the course of the last, I don't know, 30 years or so, hundreds and hundreds of people have been developing these things called packages, which are similar to like an add-in. So like in Microsoft Excel, you'd have an add-in, right? Well, a package is just an add-in to R that does cool other stuff. And so this one is called DT, and it has a function called data table. So let me go in here real quick how I like to install a package. So when I'm going to use a package in some of my code, I like to first of all ask the question, has this package been installed? In other words, there's this big repository of packages called CRAN, C-R-A-N, CRAN. And it just is a big database of all these different packages. And this function here, install.packages, goes out to CRAN and gets it and downloads it and then puts it on your computer so that R can use it. All right, well, what this first bit right here does is says, do I need to install this package or has it already been installed? All right, and so it says, if it has, I know the way this is written is a little weird. It's just the way it has to be depending on how these functions return. And if you want to know more about them, you can look up the help on the function require. We can talk more about if statements later, but I don't want to get into that right now. What it's going to tell you is it's simply going to ask, do I need to install this package? And if the answer is yes, I do need to install the package, it then installs it. All right. After this, and a function that should be here that I don't have here, but is actually I've got going on in the background, is a function called library, L-I-B, and I never can spell library. And this is all lowercase, by the way, L-I-B-R-A-R-Y. I always want to drop an R or something. I think that's library. You spell library correctly. And I'm going to put DT here. All right, that actually loads the package so that your current software, your current program that you're writing, or your current code that you're doing, your current analysis can run it. Okay, so this function library does that. Now, for the most part, I'm going to help you with that. I'm going to take care of most of that stuff in the homework assignments and whatnot, but you need to know this too. So it'll be there, and we'll just keep hitting little bits at a time. All right, and then I want to show you one other thing that I like to do in my notation for teaching, and that is this little bit right here. So when I reference a function, all right, in this case it's data table, and that's what makes this look so pretty. If I just wrote head food, it'd print out and it'd be nice and be fine. It just wouldn't be quite as pretty. But that data table function comes from the package DT. Now if I load the package DT, I don't really have to have this, but I like to put it in there when I'm teaching because then you know where that function came from. So as much as anything, that's a way for me to communicate to you where that function came from. Now, there are reasons why you may want to specify what package to pull a function from, but well, we'll talk about that later. Okay, so here's what our data looks like. We have food expenditure and we have income. And we have this over a number of observations. So, bada bing. Okay, so let's estimate a linear model. All right, to do that, we're going to use the LM function, or linear model function. And that's going to use something called OLS, or ordinary least squares. Basically, what that's going to do is it's going to take and draw a line through your data such that it minimizes the squared error. So the error is the difference between the line that it draws and the actual data point. So we take all of those. Now, if we did that exactly right and added them all up, they'd add up to 0. So that doesn't work. So we have to square them all. That way they won't all add up to 0 because all the negatives then become positive. And then we want to minimize that. Now, in a little bit, we're going to talk about some of the assumptions of linear regression and when that is what's called BLUE, best linear unbiased estimator. In other words, that's the best you can do in terms of estimating. It's the best one. And under certain assumptions, we can prove that it is the best estimator for our model. But for right now, ordinary least squares is the methodology that LM is going to use, and LM is the function that we have. Now, LM has some weird, in my opinion, weird syntax to it, and we'll talk about that as we go. But that weirdness is also actually really kind of convenient because there's a lot of little shortcuts that we can do that make it a lot easier to do some stuff that's actually pretty laborious if you don't have them. So so some other packages I've used are well, it's not harder, it's just a lot more typing. So we'll go through that a little bit as we go, but not just yet. For right now, we're going to keep things really, really simple. And so we want to estimate the model. We have food expenditure. And that's going to equal a constant. Right? And here I'm going to put a little hat on it because we're estimating it, plus another coefficient times income. And we're going to estimate these two betas. And the way we do that is with LM. So the first thing we want to do is we want to take and we're going to store our linear regression inside an object. Now remember, mod 1 here is just another one of those boxes. It's like food, only instead of holding a data frame, this box is going to hold a linear regression model. And so, you know, it's just like any other box. It can hold lots of different types of things, right? And that's what we're doing. So we're going to use this assignment character, all right, to take the linear regression that we estimate and stick it inside of mod 1. And that turns out to be really, really convenient because we're going to be able to do cool stuff with that later. All right, the next thing we're going to do is we need to put in here our formula. All right, so this first argument of the LM function is the formula. All right, and the first thing we need is our independent variable, or I'm sorry, our dependent variable. That's our y variable, what we're trying to predict. Then we're going to put in a tilde. All right, the tilde is, you know, that key up in the upper left-hand corner of the keyboard. It's over the right tick, so it looks kind of like this is what the key looks like. You have to push shift to get to it. It's kind of like a wavy dash. That's an important character because what that's going to do is that's kind of like the equal sign in our model equation. So this is the left-hand side, this is the right-hand side. Then R is very clever. It's just going to assume that you need a constant because, well, when you do regression analysis, you need a constant. Basically, here's my rule. You always include a constant unless you have a really, really good reason not to, and then you put it in anyways. So it just assumes you need a constant, and you list your independent variables. You'll separate those with pluses, but for right now, we only have one because in this chapter, it's simple linear regression. So income. Then finally, you tell it where to find these two variables. So we have a data frame that we named food. All right, so we give it the box that has our data in it called food. And here's another really cool thing about R. It uses what's called named arguments. So instead of having, like in Microsoft Excel, how you have to remember the order of the arguments for each function, you have to put them in the right order, and that's how the computer knows which one to pick. In R, the order doesn't matter as much if you tell it what argument it is. So in this case, I'm going to tell it the data equals food. And I think it does two things. It makes it so you don't have to remember the order. And two, it makes it so that it's a lot more readable. So if I didn't have this in here, I would just have this formula and then food. Okay, well, food's great. You know, I'm recording this in the morning. Breakfast would be great. You know, a little brekkie, good for us, right? But what does that have to do with my L? Oh, food is the name of the data frame. Okay, that kind of thing. These named arguments is actually really, really cool. Now, here's the problem, though. This in and of itself isn't actually going to display anything. You're going to run that, and it's going to look like nothing happened. Well, something did happen because the model got estimated and got stored into mod 1. It's just there's nothing there to tell it to print anything out to the screen for the humans. So that's why we're going to use this summary function. All right, and so this is going to be a very common pattern that we're going to do. We're going to estimate a model, and then we're going to use some kind of summary function to display that model. So let's go ahead. That's what the data looks like. Let's go ahead and see what its output looks like. So this is the output of that code. So we estimated our linear model, and here's what's neat. The first thing it's going to do, summary is going to do, is going to give you the call. In other words, that's the command you used in order to get all of this stuff. So this is the LM function that you typed in. And then the next thing it's going to do is it's going to give you some information about the residuals. Now, remember what residuals are. Those are what's left over, what's left unexplained in our data. Okay, so we'll talk about residual plots a lot. I mean, one of my top 10 things to do in order to avoid being fired for you doing something really stupid with data is plot the residuals. It won't catch everything, but the really big, monumentally stupid mistakes that, you know, really basically do not pass go, do not collect $200, just clean out your desk. At least some of those you should be able to see with a residual plot. And I have a few stories I can tell you about that, but, you know, later. Okay, the next thing that we have in here is the coefficient matrix. Now, what's really important to remember about this is this isn't just some abstract table. We've actually estimated a formula. So that formula is food expenditure equals beta naught plus beta 1, and these are both hats because they're being estimated, income. Okay, now that is beta naught. That is beta 1. So we should think about this as an equation. So I take 83.42 plus 10.21 times income, and I will get my estimated or food expenditure hat, you know, my Y hat. That'll give me my predicted value. And of course, like for example, the actual value, so food expenditure less this is my residual. All right, yeah, that was a bit messy. Okay, so coming back to it, that's what we have here. Now let's look on here. Each one of these is a random variable. It's an estimator, and so it's going to have a standard error. All right, now it took me a while to figure out what the difference between a standard error and a standard deviation and what that terminology really was all about, and it's really, really simple. A standard deviation is a measure of variation in data. So actually observed data or data from a population. That's fine, either of that. So the actual data. Now, I could, though, take from that data and make some kind of estimate. Right? I'm going to do some kind of calculation, like the mean or the median or the standard deviation. Yeah. So your standard deviation has a standard deviation, and we call it a standard error. All right, that's like something you should say 10 times fast and see if it messes you up. In any event, we have these estimators of different characteristics of the population about the data. In this case, we're getting information about the relationship between income and food expenditure. Okay, great. Well, all that's there. These are random variables. That means they come from some kind of population. That population itself has characteristics. We talk about the characteristics of a population or of its distribution. All right, so the distribution of a population is one major thing that we use to describe that population of whatever it is. And the characteristics of that distribution we call moments. All right, so it's the moments of the distribution. In fact, we can identify a distribution by its moments. So each distribution will have a unique, what's called moment generating function. All that stuff aside, doesn't really matter. This is the average spread of these variables because they're themselves going to come from some distribution. It happens to be a t distribution. And how wide this is measured here. Okay. And that's what that standard error is. We can use the standard error to come up with a t-value, or sometimes called a t-ratio. Because you'll notice that the coefficient divided by the standard error equals, let me do this better, the coefficient divided by the standard error equals the t-ratio. All right, not too tough. It's just those two divided by one another. And there you go. Equals. And so Well, that's kind of cool. And this t, it's called a t-value or a t-ratio because they have a t-distribution, and we can use that to perform hypothesis tests. Now, we're going to talk about hypothesis testing a little bit later. Generally speaking, just remember, if the p-value is small, we reject the null. Okay? Yeah, see that kind of really terrible poetry, right? If the p-value is small, you reject the null. Actually, you reject the null, but you know, if I say it wrong, it kind of rhymes. Small p-value means reject the null hypothesis. The null hypothesis in this case is that these guys are equal to 0. In other words, the variables don't matter. Well, first of all, when we look at the intercept, we just generally don't care. You're always going to put a constant in. It doesn't matter whether it's significant or not. There's some really major damage that happens to these models if you don't put a constant in. So you really, really, really need to know what you're doing if you leave that out. So basically, even after this class, you don't know enough to leave it out. So put it in. All right, next, we assume that this variable doesn't matter. The income has no impact on our food expenditure. And because it has no impact on our food expenditure, we want to prove otherwise. All right, so we assume it doesn't and then show, oh, well, wait a minute. Well, if it really had no impact, finding a coefficient this big would be really, really unlikely. This is 1.95 times, and this e to the negative 5 means times 10 to the negative 5th, or 1.95, and then we're going to go 1, 2, 3, 4, 5. So 0.12345. So 0.00000159. We'll multiply that by 100 to get it into percentages. So 0.00195%. So we're not even 1%. We're at like the 99.9 percentile, or percent confidence level, that this is significant. So we conclude that yes, income does have a statistically significant impact on food expenditure. That's not so cool. All right. I mean, it's kind of, yeah, big deal. We know all that. All right. A few other things we want to look at, and I might wait and talk about some of this later. But in fact, I will talk about some of this later. The one I do want to talk about, though, is this one, the residual standard error. This is also in other packages called the standard error of regression. Okay, so those two are the same thing. This is the standard error, or what it is it's a standard deviation of the residuals, which under the assumptions of linear regression is equal to the standard deviation or the standard error of y hat, because our y hat, or our prediction that we're going to talk about later, okay, that's a random variable too. And so that's this standard error of regression, or the standard error of the residuals, or what this calls a residual standard error. We'll use that later. It's oftentimes referred to as sigma. Okay, the next thing we want to look at is this multiple r squared. In fact, I think I will come back to that, but this is the coefficient of determination. I think I have slides on that, so we're going to come back to it. All right, and then finally, we have an F statistic. This F statistic for simple linear regression is not particularly interesting, because this test is algebraically equivalent to this test up here, because there's only one predictor. So we'll come back to the F tests a little bit later. Okay, so let's do a little bit more work. Let's plot this model. Basically, it's always a good idea to do that. We're going to use some functions here. Right now, we're going to stick to base R. Base R means we're not using a package. There's a really, really awesome package called ggplot that we could use to plot this. There's a few other packages out there too that do some really cool plotting, but ggplot is like the quintessential awesomeness when it comes to making data visualizations. And once you get used to it, you're going to love it. But For right now, we're just going to use the basic plotting function that's been around for decades in R. It's not the coolest, but it'll work. All right. And what we're going to do is the first thing we're going to do is we're going to grab the coefficients. So that B1 there, that's my constant. And the B2 is my coefficient on income. All right. I know I'm used to writing the constant as B0, and this textbook calls it B1. And so I might go back and forth a little bit. Sorry for the confusion. But in any event, so we're going to grab this coefficient, mod 1. All right, that's our thing. And this is where it comes so cool that we can just store our model inside an object, because now all we have to do is go grab that. And for right now, just use this notation. We're going to use this double bracket notation. It doesn't exactly make sense yet. There's logic to it, but I don't want to explain it now because it'll just we'll go too down in the rabbit. We'll go get too lost in the weeds. So what I want you to do is just remember, I can use this coefficient function to get the list of these coefficients, and I can access each one of them here and store them in variables. So these are both objects that are holding, in this case, a single number. All right, then what we're going to do is we're going to use the plot command, and we're going to say, okay, I want you to plot food income, and then I want you to plot food expenditure. So put on the x-axis income, put on the y-axis food expenditure. So we're just going to get a scatter plot. All right, then we're going to label everything. And then it says type. So that type P, that means I want a scatter plot. Give me points. And the final command on here is I'm going to use AB line to draw a line that has an intercept of B1 and a slope of B2. And what am I going to get? That guy. All right. He doesn't look too pretty, but I'm going to tell you there's a lot of information here. It's really worth making sure we draw something kind of like this. The first thing I'm going to notice is, well, look at this. My plots. All right, they kind of make a trumpet shape. They make a triangle shape. Well, that's not something I really want. What I really wanted to do is I want to be able to see my dots all kind of surround my regression line, which is this line in the middle. And I want it to be nice and even and band and, like static around this line. And well, it's not that. So that tells me, hey, I've got some more work to do to get this to be a good model. In fact, this has a special word. It's called heteroscedasticity, which we'll talk about later. Overall, the linear relationship, other than the heteroscedasticity, doesn't look too bad here. But the heteroscedasticity tells me, hey, I'm probably missing something, so that I should continue to do a little more analysis. But a plot like this is really, really handy to look at because oftentimes you'll pick up problems that you wouldn't have picked up before. All right, so let's look at some prediction. So we know that this model could be improved, but we're trying to keep things simple, and that's part of why it needs some improvement is because, well, it is probably just a little too simple. So what we're going to do now is we're just going to keep using this simple model, and we're going to make some predictions. And there's a great function called predict in base R that you can use to do that. Now, what predict is going to do is it's going to calculate lots of information about a prediction for you. So you're going to put in the new data, all right, or the data that you wanted to predict it for, and it's going to spit out all kinds of information about that prediction. But to do that, we need to create a data frame. So we need to create a data frame that holds the new data in it. And what that new data is going to be is our values of income that we want to predict for. So what I'm going to, and you could do more than one value. For right now, I'm going to make a data frame that has one observation of one variable in it. You could do more. All right, that's fine. And we can talk about the syntax for doing more. There's lots of different ways to do that. But for right now, we're keeping it really, really uber simple. And we're going to do one observation and one prediction. And so let's look at this. We need to store this in a data frame. And we're going to use the data.frame. And here's something else to note in R. Spaces in general are bad in R. We just don't use white spaces for the most part. There is a little bit of white spaces, but for the most part, definitely not names or variables. And when you get into trying to do this with Windows and you have to deal with File names and paths that have spaces in the paths, it's a real pain in the arse. Spaces in file name paths, where you look at, you save a file and you put white spaces, they should just not be allowed. Should never have been allowed. I don't know why Windows ever did it, but oh well. In any event, in general, we'll replace a white space with a dot in R, which if you've ever done any programming in any other languages feels a little weird. I know it seems weird to me, but that's what they did. All right, so the dot is generally speaking, is a space. A white space is the way you can interpret that. And so we're going to make a new .data. It's going to be our frame. That's our box that we're going to put this in. We're going to use data.frame, and we're going to give it some information, and it makes us a data frame. And in this data frame, we're going to have one variable called income, and it's going to have one observation of 20. Okay. All right, let's keep going. All right, now, so you see these plots, these boxes here? This is what you would get if you didn't use that DT function or that data table function. They're still okay. They're just not quite as pretty, right? So that's what all that was. It was also a good excuse for me to talk about what a package was. In any event, so we're going to look at this. All right, we're doing predictions based on model 1 with our new data, and we're going to do 2. One where our interval is a confidence interval, and one where our interval is a prediction interval. And what the heck is the difference there? Okay, well, think about it this way. I am going to predict what food expenditure will be if it's 20. Now, if I want to know what and in both cases, my prediction is the same. All right, I'm getting about 288 units. Now, what's the difference though? If I want to predict this for a group, so what is the average consumption for a group of individuals with an income of 20? All right, well, I'm going to have some that's high, some that's low, and they all balance out to an average. And that's a lot easier to predict than what one individual would be. And so this is, what would a group, a big group, who all make 20, what would they average? And that's what this confidence level is. And notice, it's much narrower than my prediction interval, because what the prediction interval does is it says, okay, that one guy right over there. All right, yeah, no, not you, right? That one guy who makes 20, what will his food expenditure be? All right, if you want me to, I can also pick another one over there. What will her expenditure be? All right, we can do that. But in any event, what will that expenditure be for that one individual? Well, that's a lot harder to predict. All right, because I don't have any, highs and lows. Is he one of the high persons that's up here? Is he one of the low persons? I don't have all that stuff to kind of balance out in an average like I would if I were predicting for a group. I'm predicting for a single individual, and so I'm going to be less certain, and so that's what this prediction interval is. And that turns out to be really useful in a lot of cases. Okay, so let me keep going. Almost done. So let's do something that I think is just really, really useful. Prediction probability. So let's predict the probability of outcome of a range of outcomes. All right, so have you ever heard the fact that, weather forecasters are never wrong? Did you know that? Weather forecasters are never wrong. It's true, they're never wrong, right? How is it that they're never wrong? Well, they say there's a 20% chance of rain. I mean, think about it, this is quite a racket. What the heck? There's a 20% chance of rain. This is awesome. If it rains, they told you, well, there was a 20% chance of that happening. And if it doesn't rain, well, there was an 80% chance it wasn't going to. All right. So, I mean, this is awesome. They're never wrong. This is cool, right? Well, we can pull the same trick. In fact, this is what really good forecasters do. They split the forecast up into these kind of discrete sets of nature. All right, states of nature. Okay, so like forecasting the weather, rain or not rain. All right, I have two different discrete sets. Now, I'm not trying to figure out, well, how much rain would there be? 0 inches to 3 inches. That's a little harder forecast. And yeah, that can be useful. But if what I could do is I could split it up into really actionable decision-making might be, is it going to rain or not? Because I'm going to take an umbrella if it's raining and not if it isn't. Okay. And so I just need to know a yes, no, is it going to rain or not? So I split it into these two categories, and then I find a probability of each one. And this is actually a really, really powerful forecasting technique. One of the ways to look at this, if you want to look at a really cool website that does this, especially for political stuff, go to 538.com. All right, 538. Probably everybody's heard of that one by now. It's a organization, a site. It was begun by a gentleman named Nate Silver, who was a very, very popular, very successful forecaster. And this is a lot of what they do. They basically break things up into different possible scenarios and then figure out what the probabilities of those scenarios are under certain levels of assumption. So this is really, really, this can be a really, really powerful way to, one, help in decision making, and two, boil down a lot of complicated analysis into a really concrete thing that you can explain. So let's keep going. I think I said all that. So let's make an example. So let's figure out what is the probability that a person will spend at least $200 a week on food if they have an income of 20. Let's find that out. All right, how can we do that? Well, the first thing we're going to do is we're going to get that estimate. So we got this y hat. All right, and we know what that is. It's approximately 288, okay, approximately. But that's a random variable, and it has a t distribution. All right, this is really powerful. We know a lot about this now. You know, we can figure things out. We can calculate the probability using a function called PT. Now, in base R, you have several different distribution functions. One of them, if you know the quantity or the t-stat or the z-score or whatever, and you want to know the probability, you put p and then the distribution, and then you have a function. And that pattern works for normal distributions, chi-squared distributions, t distributions, f distributions. Oh, I think there's a few other more exotic ones that works for too, but you get the idea. So it's kind of a common syntax there. It's really quite nice. So we need to know, well, what a t-stat would be for a prediction of 200. And so what that becomes is, I want to know 200. And so I just subtract off my 288, which is my value that I have from my prediction, and divide that by the standard error of prediction. And I don't remember what that is. Okay, so here's the problem though. R doesn't really do this very easily. So I have to do a little bit of a hack in order to get this standard error of prediction. It's really, really annoying because you know R calculated it because it does calculations that require it and returns them. But it doesn't have an easy way to access the actual standard error prediction. So we have to do a little bit of blah, 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 blah to get there, right? And so what I've done is I wrote a couple of functions for you. I don't know why there's a space there. There shouldn't be, but oh well. Second edition of all of these slides, I'll get rid of that space. Okay, in any event, let's keep going. I wrote a couple functions for you. Here they are. These slides are up on the course website, so you can just copy and paste them. I'll probably include them in your homework too if you need them. So you don't have to worry about these. If this all makes sense to you, great. If this is all what is going on here, don't worry about it. All right. The bottom line is all you have to do is pass to this predict.probability function, your linear model, your new data, what alpha level you want, so what level of significance you want, and whether or not, and what you want to know. Do you want it to be greater than or less than? All right, the default here is greater than. And then you want to know what do you want to be greater than? So the value. So in this case, we'll keep going and I'll show you what it looks like. I'm going to put in model 1. I'm going to put in my new data. It's going to be this data frame where income equals 20, easy peasy. I'm going to leave my alpha level at 0.05. That actually isn't that important for what we're calculating right now, but There is some, this is going to refer to a prediction interval, and that's where that comes in. I want to know whether it's greater than 200 or not, and I want to know whether it's 200. Oh, and I made a little mistake here. That should actually be an equal sign, and that should be an equal sign. Generally speaking, when we're doing arguments inside of a function, we use the equal sign. Pretty much everywhere else, we're going to use that assignment character. So yeah, these should be equals. In this case, I got away with it. It worked, but don't do that because sometimes it won't. Yeah, it's a little arbitrary which one we use, but don't get too worried about it. For the most part, at the top level, use an assignment character and really only use equal signs here inside of a function. So I have named arguments and I'm telling it what that argument is. But here and here, those are wrong. So make sure you use equal signs there. Amen. Okay, keeping on going. Then I'm just using a little fancier function cable. It doesn't matter. It just turns this into a nice table. Okay. And I can control things like whether it's left aligned or right aligned and how many digits I'm displaying. That's all is doing with this cable function. You don't really have to worry about it too much. But in any event, coming down here, we see my value is 200. My probability of being greater than 200 is 0.83. So I have an 83% chance of having a person who has an income of 20 having expenditure greater than 20 or greater than 200. That's pretty darn cool. Let's say you have to decide, okay, the average income in community X is 200 or is 20. I need to have the individuals spend at least $200 a piece on food in order to make money on them. And so what's my likelihood of being successful? 83%. All right. Okay, that was really poorly posed, and I did that right off the cuff. And if you really listen to what I just said, you'll find all kinds of mistakes in it. So yeah, I get it, but you understand the basic premise, right? So let's keep going. And let's visualize this. So I'm going to use this probability.prod plot, which is really more just to demonstrate what's going on. So right down here, this is a t-distribution, and t-distributions are always centered around 0. That's just the way we set them up. And so this is basically our 288. That's what our prediction is. This was our value, 200. And this shaded area is the 0.83, which is the probability of expenditure being at least 200 or greater, right? And that's what we just calculated. That's what that 0.83 is. It's not, this prediction plot isn't that cool. I mean, it's not that important, but it does help illustrate what it is that we're doing. Okay. Oh yeah, here, sorry. I have some explanation of that, but I just explained it, so that's good. Hey, so cool. Awesome sauce. See you next time.